previously we discussed how to construct a custom transformer, some step we need in our workflow to apply some transformation, some process on our data set prior to passing it down to a downstream model, usually a predictor. So that's one aspect of creating custom estimators. We also need to understand how to construct custom predictors, specifically regressors and classifiers. Those are two different types of predictors we have in the scikit-learn environment. So it's going to be a very similar approach. First thing we got to do is import the regressor mixin. Remember, this mixin is going to define what type of estimator do you have. In this example, we're going to show you we want to construct a custom regressor. A regressor is a model, a predictor that's going to predict continuous values. Think of it, we would use it to predict housing prices. Those are continuous values. We're not trying to predict categories or classes. We're trying to predict a continuous value. So import the regressor mixin. We're going to define our custom regressor. In this case, we want to create a very simple custom regressor. We want to create one that's always going to predict a single value for all the observations based upon the mean value of the training set, the mean value of the labels of our training set. We'll call that mean regressor. We're using camel case as before. It's going to inherit first the base estimator, that base functionality that defines all estimators in scikit-learn. Then it's going to inherit the regressor mixin. So now it's a regressor. It's an estimator that is a regressor. All right. The first method we have to define is the init method. This is a method that's going to initialize any attributes for any objects we create from this class. In this example here, there are no attributes we want to create for the object. So it's going to be an empty method. So we'll just use the pass keyword. So we use the pass. That just says, hey, there's nothing in here. Don't worry about it. We have to have it. If not, we'll raise an error. So in fact, you can just omit the init method for this example. I usually like to keep the init method even though there's nothing going on there, so I'll put pass. I think it's just easier for me to see that there is an empty init method if I be explicit about it, but keep in mind we don't have to have the init method in this case. We can simply omit it. But if you do include it, make sure you use pass inside the method. Okay, so now let's go to the next method we have to define. Let's define the fit method. Now, as I discussed before, as I said before, this regressor is going to calculate the mean label value of our training set and use that to always predict for any observations. It's a mean regressor. So in this fit method, notice it's going, the first parameter is self. Don't forget about that. That's a common mistake. The self refers to the object itself. The next two parameters are x and y. So x is our data set, our feature matrix, rows and columns, and y is our labels, the true value corresponding to all our observations. For this example, we're not going to make use of x. We're simply going to use the y's. And we're going to use NumPy's function called mean to calculate the mean value of our labels. Notice, even though we don't use x, we got to make sure we include it in the method signature. So make sure we have both x and y. I want to point out this is a bit different from the transformer. In the transformer, if we didn't use y, we set y equals none. Usually for predictors, you'll have to make use of both x and y. So that's why we don't say y equals none. All right, so we calculated the mean value. Now, since we want to use this mean value for predictions, we got to be able to store it. Remember, one way you can view an object is some entity that's going to store data, store information, as well as has functions tied to that object that can work upon your object. So we're going to store this result into an attribute of the object called y_mean. We'll make use of it when we do prediction. So you can think of the point here, what's going to happen here in the fit method are all the things that I need to calculate so I can make a prediction. What are the coefficients? What are the model parameters? What are all the things I need to calculate so I can make a prediction using this model? It's a mean regressor, so I need to calculate the mean of the labels of a data set. And I store it in yMean. As before, don't forget that we want to return self in our fit method. This is a common mistake where people forget to return self. The fit method is always going to return the estimator back. It's going to give you the estimator back. In fact, if you forget about self and you're working with pipelines, you might get an error saying some problem with none. You might get a none. That's usually happens is because you forget to return self. Okay. So now we define the init method, which is empty. We define the fit method, which calculated our parameter of interest to make predictions with our mean regressor. Let's actually go ahead and define the predictor method, the final method. So in that method, it's going to accept self, customary, and the only other parameter besides self is x, which is the data set we want to make predictions on. So for this mean regressor, for all the observations, we got to make a prediction based upon that mean value we calculated during the fit method, when fit was invoked for our custom regressor. So what we got to do first is we got to calculate how many observations are in our data set. Remember that convention we talked about? We have a data set. Data set is a matrix, has 2 dimensions. What dimension corresponds to our observations? The rows is the dimension that corresponds to our observations. And the columns, remember what the columns refer to, what they're associated with? The columns in our data set represent the features or attributes or characteristics for all our observations. So what we're going to do here in this predicament, if I can break down this code, is that we're first going to get the size of the 0 dimension of our matrix. So if I go back here, I can sketch out how this looks like. Remember, X is a matrix. So we have rows and columns. And every NumPy array has a shape attribute, which will tell us the size of dimensions for all the dimensions the NumPy array has. So one thing to keep in mind, using 0 indexing or that 0 convention, the rows, the number of rows is going to be dimension 0. The number of columns is going to be dimension 1. So this is dimension 0, and this is dimension 1. So if I want to find out how many rows I have in my NumPy array, I do x.shape, and then I ask for the 0 index. So that will give me the number of rows. So now I know the number of rows, number of observations. I want to construct a NumPy array of nothing but ones. I can achieve that by using the np_ones function. So I say construct an array that has the size of that array, it's going to be 1 dimension, has the size of it is going to be the number of rows my data set had. So now I construct a vector, a 1-dimensional array of nothing but ones. If I want to have, well, if I want that array to populate to have a value other than 1, I can simply multiply it by a scalar. In this case, that scalar is going to be the mean value that I calculated, that I figured out during the fit method that was stored in the attribute called yMean. So in other words, what we do with the np_ones is we construct a 1-dimensional array, nothing but 1 values for all the number of observations we have, and then we simply multiply it by some constant value. So if I do this operation, we end up having a NumPy array in which all the entries are y bar, the mean value that we calculated and we stored during the fitting process, where we invoked the fit method of our custom estimator, custom regressor. And that gets returned. So notice there in the predict method, we want to return the predictive values, the values we predict with our regressor. All right, let's run that, and of course I forgot to run this block code there, so I'll run that, and sorry about that. I talked about them but didn't run them. Okay, ran those blocks, so now I have my mean regressor defined. So let's actually use it. So we'll create an object. I'm going to call it mean regressor from our mean regressor class. Notice I don't pass any parameters to it when I construct the object because the init method is blank. Nothing going on there. Call the fit method. When I call the fit method for a predictor, I pass the x and I pass the y's, the feature matrix, along with the labels corresponding to the true value for all the observations in x. Once I fitted my mean regressor, now I can use it to make predictions. That's what I do in the next line. Make a prediction, predict a value for all the observations in x. I'm going to print out that output. Now I'm going to also use the score method of our regressor. Now, notice I'm going to use this score method, but if I look at the definition of my mean regressor, notice I didn't define the score method. I defined the fit method, the init method, and the predict method. I didn't define the score method. So what do you think is happening there? This is where the concept of inheritance is important. When I define this class, I'm not creating it from scratch. It's being constructed based upon the base estimator, then I add the mixin. So now I have a class with some sort of functionality to it. Now, with this new class, with this child class, I can define additional methods to them. But by inheritance, this class is going to inherit all the methods that these two classes have defined. So the regressor mixin, if I inspect the code of the regressor mixin, it has already defined the score method. So I don't need to define the score method. It inherited the original score method of the regressor mixin. It inherited it. If I want to overwrite that method, use my own custom method, not the one it inherited, then I would go ahead and define it when I create my child class. So if I want to have a score method that deviates from the inherited one, then I would just say def score and define my score method. And then define my custom score method. But I don't want to define my custom score method. I just want to use the one it inherited from the regressor mixin. So I'll just comment this out. But that is why when I run this cell, I can use the score method and it actually does something. It's going to return me a score because it's using the one it inherited. So now I do my predicted values. So these are my predicted values. So it's a NumPy array. Notice that they're all the same, which makes sense because that's what we define our regressor to do. Always predict the same value regardless of the attributes of the observations. Same value for all the rows, all the observations in our data set we pass when we invoke the predict method. And the score, we get an R-squared value of 0. We'll talk more about what this R-squared value means, but you want your model to have an R-squared value closer to 1. An R-squared value of 0 means your model did just as well as a model that always predicts the mean value, which is, by definition, what our regressor does. The regressor we defined in this exercise, in this example, in this lecture. So it makes sense that we get an R-squared value of 0 for this custom regressor.